Sarah, and thank you everybody for being here today. My name is Rachel, and I am an astronomy graduate student at Georgia State. And we're really excited. We have 3 activities to do with you today. We're going to start by doing a night sky tour. Then we're going to talk about life in the universe and make some aliens. And then we'll complete our activities today by talking about sound waves and making paper telephone cups. So we are utilizing both the chat window and the Q&A. And Katherine and Dan, if you guys want to wave, these are our moderators today. So they'll be either speaking up and letting a question come out, or they'll be typing responses in the chat window. There are quite a few of you, so we're not going to probably be able to answer every question verbally, but we'll do our best. So if in the middle of a talk you have a question, please post it either in the chat or the Q&A, and we'll be very excited to answer those for you. So I am going to go ahead and share my screen, and we're going to start with our star talk. All right, and I think everybody can see my screen. Can you guys nod for me? Perfect. So I wanted to show you, we have, for our 3 activities, we have 3 PDFs that go along with them that you can find on the registration page. And we'll kind of go through each of them for each of the activities. So let me minimize this. And now we will start with our night sky tour. So it is not dark yet, so let's fast forward time. This is one of the benefits of being in a virtual place, is that I can control time and space and can make things go as quickly as I like. So we're going to fast forward time to about 8:30 tonight. And we stopped at about 8:20, but we're facing south right now. And I always like to start my star talks by putting up these stick figures here. And usually when I ask people what these are, they tell me that they are constellations. But if you're seeing stick figures, these are actually things called asterisms, which are just patterns that were made up to tell stories, to find directions. If we want to see what constellations look like, they actually look like this. So the same way that the United States is split up into 50 states, the nighttime sky is split up into 88 constellations. But the idea of a constellation is not a new thing. And if we're thinking about the way that the constellations got their name, and for the official ones that we have, we use Greek and Roman mythology, but in every culture around the world, they all have different mythologies, different things that they saw in the nighttime sky. But for what the constellation names are today, they were imagining things that looked more like this, where there were hydras and unicorns and bunnies hanging out in the nighttime sky. So taking all of this down, and we'll talk a little bit more about what people saw in the nighttime sky in a minute. I actually like to start my star talks in the north. So we're going to go ahead and give ourselves a little bit of a spin so that we are facing north. And I'm going to switch my controller to pick up the asterism of Ursa Major, or the Big Bear. And if you look at the tail and the back of the Big Bear, you may notice a shape that looks a little bit familiar. And this is the Big Dipper, which is probably one of the easiest asterisms for us to find in our nighttime sky. And looking at this, I want to know what your guys' opinion is of what this group of stars looks like. So this will be our first poll that we will activate. And it's going to tell you to pick, this looks like a bear, this looks like a plow, this looks like a wagon, this looks like a boat rudder, or it looks like a ladle. So what do you guys think this looks like? And we'll give about 30 seconds for people to vote. Oh, and it looks like there's a pretty close race for 2 of these. And we'll do just a couple more seconds. All right, and with 82% of you voting, it's a tie between that it looks like a bear and it looks like a ladle. So we'll go ahead and end the poll. And actually, every person who voted, you all picked something that somebody thought this looked like. So if you picked bear, you're living in the Mediterranean or with indigenous peoples in North America. If you picked a plow, you might be living in England or Ireland. If you picked a wagon, this is what people in Germany saw this as. If you picked a boat rudder in Vietnam, this is what Vietnamese culture saw the Big Dipper as. And if you picked a ladle, this during the time of the Underground Railroad in American history was seen as a ladle. So this is awesome and great job, everybody. And the reason that we like the Big Dipper so much is because we can use it to find a cardinal direction. So we can actually use it to find our North Star Polaris. So we're going to go ahead and put the stick figure away. Again, here is our Big Dipper. And using Dubhe and Merritt, which are the front two stars of the Dipper, we're going to go in a straight line and run into this star right here, who is Polaris, our North Star, who makes up the tip of the handle of the Little Dipper. Now, this is really cool because if you're ever outside and you need to find directions, you can find the Big Dipper, you can find Polaris, and you know that you're facing north. And Polaris is going to stay put no matter what kind of movement we see in the nighttime sky. And we actually see two types of movement in the nighttime sky, the movement from day to day, and then the movement as we go through the night. So let's take a look at both of those. So again, having control of all of time and space, I'm going to fast forward time a week and then rewind time and see how the stars jump a little bit as we go forward each day. So let's go ahead to March 20th, which is a week from now. And then we'll back up again to today. Now, this movement that we're seeing is the movement of us moving in our orbit around the sun. And because we're moving pretty quickly through space, the stars rise 4 minutes earlier every night. And this is why we see different stars in the sky at different times of the year. The other motion that we see is the night to night motion. So now we're going to stay in tonight and we'll fast forward time towards tomorrow morning. And we're going to see everybody is moving around in a circle, but Polaris is staying put. And that's because Polaris is basically right above the Earth's North Pole. So let's back up time to about 8:30 again. And hopefully nobody's getting too dizzy from this. And we'll pause there. And this is just the Earth spinning on its axis, which it does once per day. Now, this is really great for us right now, but Polaris hasn't always been the North Star, and Polaris won't always be the North Star, because while the Earth is spinning on its axis, it's also wobbling or precessing. So let's flip over to a little video and we'll see what that looks like. So in this, you're going to see two different motions. You're going to see the Earth spinning on its axis, and you're also going to see the Earth wobbling as it's spinning. So let's watch that happen. And this is what the Earth is doing. And it takes about 26,000 years for the Earth to precess once on its axis. And here is a little map that shows time in this circle and different stars. So we're in 2021, which means Polaris is the North Star. But if we went back in time, and I really like history, to the time of the ancient Egyptians, which was about 3000 BCE, when the pyramids were getting ready to be built, Thuban was actually the North Star, which is in the constellation of Draco. So let's find Thuban. We'll go ahead and deselect Ursa Minor's stick figure, and we'll select Draco's stick figure. And Thuban is actually this star right here. So from 3000 BCE to 2021, the North Pole of the Earth has moved this much across the sky. And that's pretty cool because most things that happen in space don't happen on people timelines. So the fact that humans are able to watch this happen is a pretty cool thing. And the way that we found out that this was happening is that because there wasn't TV, people were like, you know what we're going to do? We're going to write down where all of the stars are and keep track of this. And a Greek person named Hipparchus kept his records and then went back and looked at records from 100 years before that and then 200 years before that, and noticed that at the fall equinox, that stars were in different places. And this is where we started to understand that not only were we spinning on our axis, but we were also wobbling as we were moving. So let's go ahead and put Draco down. And the other thing that I want to point out to you is the one thing that we can see in the nighttime sky with just our eyeballs that's actually outside of the Milky Way galaxy. All of the stars that we see, the fuzzy nebulas that we can see, these things all live inside our galaxy, but with just our eyeballs, no help from a telescope, no help from binoculars, there's one thing that we can see that is outside of our galaxy. So again, using Dubhe and Merritt, we'll find Polaris, and then we'll take a straight line over to Cassiopeia, who is shaped like a W here. And Cassiopeia was a queen in ancient times, and this is supposed to represent her throne. And using this bottom part of the throne, or the W shape, we have a nice little arrow that points us to this little fuzzball right over here. And this little fuzzball is the Andromeda Galaxy, and it looks pretty small from our perspective, but it's actually 2 times the size of the Milky Way galaxy. And I think my favorite thing about this is that it's 2 million light years away. So if tonight we could all be together and go outside and look for this, we're not seeing the Andromeda Galaxy the way that it looks today, right now. We're kind of being time travelers because we're seeing it the way that it looked 2 million years ago when that light left the galaxy and made its way to our eyes here on Earth. So pretty much everything that you see in the nighttime sky, you're not seeing how it looks right now. You're seeing how it looked however many years in the past, depending on how far away it is, which I think is pretty cool. Now, the other really cool thing is that most things in the universe are moving away from us, but Andromeda is actually moving towards us. And in about 7 billion years, there won't be a Milky Way galaxy and an Andromeda galaxy. There will be a Milkomeda galaxy because the 2 galaxies will have combined their powers together to form one giant galaxy. And we're going to post a simulation. We don't have real pictures of this, but there are computer simulations that show what that will look like. And in the simulations, it does kind of look like an action movie, but in real life, since things are really far apart, there are not very good chances that grown-up stars are going to run into each other. But there are very good chances that the gas and the dust that lives in between the stars will run into each other. And so they will end up forming a whole bunch of new stars once the Milky Way and Andromeda start coming together, which I think is kind of cool to think about. All right, so that is, I think, the big things I want to show you all in the north. So let's go ahead and switch my cursor, and we're going to spin ourselves around to the south, kind of southwest. And I have to tell you guys, this is my absolute favorite nighttime sky because this is the place where you can see stars at all points in their life. And so I'm not sure how familiar everybody is with what stars do when they're born and how they live their lives and then end their lives. So let's talk really quickly about what stars do as they go through their lives. So here is a diagram of what different stars do. So every star starts its life in a stellar nebula, which is full of gas and dust. And when these gas and dust clouds start clumping together, this is when stars are born. And you can have average sized stars are smaller, kind of like the sun. Or you can have really, really massive stars. And depending on how big these stars are, that will kind of depend on how they're going to live out the rest of their star life. So let's pretend we're talking about the sun, who is a normal, average, middle size, middle age, a little heavy for its size, but still a great star. And what it's going to do with its life. Right now, it's taking hydrogen and fusing those hydrogen atoms together to make helium. And it will continue to do this until it uses up all of its hydrogen, and then it will puff up into a red giant star when it's starting to use up helium and some of those heavier elements. And because it only has a certain amount of fuel, it will end up running out probably somewhere around carbon and oxygen, and it will basically kind of spit off its outer layers, and you'll have a little white dwarf living in the middle that will be left over, basically the core of the star that will just kind of hang out and live its life. So unfortunately, the sun isn't going to have a supernova. It's not going to explode. You have to be much bigger than that much bigger than the sun in order to do that. So if we are talking about stars that are doing those sorts of things, we need the massive stars. And they go through the same process where they burn up all of their hydrogen into helium and into heavier elements, but they're big enough that they're able to burn or to fuse elements together all the way till iron. But no star, no matter how big it is, has enough energy to do anything with that iron. So once it has an iron core, it collapses on itself and has a supernova, so it explodes. And depending on how big the star was when it started its life, you'll either end up with a black hole or a neutron star. Now, in my research, I study black holes, and they're super cool. And if you guys come and see us out at the observatory when we're able to get in person again, come during the summertime and we'll point out a couple of black holes in the nighttime sky for you. But since we're in the winter sky, we're actually going to talk a little bit more about neutron stars. So what I need you guys to imagine is something that could fit inside of Atlanta and that can weigh about 1.5 times as much as the sun, but can spin in a complete circle 30 times in 1 second. And that's what we're dealing with when we have things like neutron stars. So yes, they're not quite as fancy as black holes, but neutron stars are very cool, and we'll talk about one in just a minute. So let's go back to our nighttime sky facing south, and we're going to go ahead and pick Orion. And Orion is great because it has a bunch of things about stellar evolution inside of it. And also you can use Orion as a guide post to find other things in your nighttime sky. So starting with Orion itself, down here in the foot, you have a blue supergiant star called Rigel. And up in his armpit, he has a red supergiant star called Betelgeuse. And if you, on the computer program I'm using, which is called Starry Night, you can see that Betelgeuse is kind of an orangey red and Rigel is a blue color. And if you go outside tonight or in any night in the next couple of weeks and look at Orion, you're actually going to be able to see those colors in the nighttime sky, because stars have different colors based on their temperatures. So red stars like Betelgeuse have cooler temperatures, and blue stars like Rigel have very, very hot temperatures. Now, compared to most things on Earth, all stars are hot, but comparing stars to other stars, some are cool stars and some are hot stars. And you might have noticed this little fuzzy group right down here under Orion's belt, which is right there. Let's zoom in on that little fuzzy patch. And this little fuzz here is the Orion Nebula. And so this is one of those stellar nurseries where that gas and dust is clumping together and making brand new stars. And in the middle of the Orion Nebula is a young group of stars called the Trapezium. And these stars are about 300,000 years old. So these are basically baby stars. I mean, they're very old to us, but in the lives of stars, these are basically brand new baby stars living here. And I can't show you a picture in this program, but Orion does also have protostars, which are stars that haven't started fusing hydrogen in their cores yet, and they have little gas disks around them. And the Hubble Space Telescope has taken some pretty cool pictures of this. So these are our baby stars living here in Orion. Let's zoom back out. And now using Orion as a guidepost, let's go ahead and put his stick figure down. We're going to take the belt stars. So without the stick figure, here's Orion's belt. Here is Rigel down here and Betelgeuse up here. The Orion Nebula in the night sky with just your eyes, you won't be able to see it, but even if you have a small telescope or a pair of binoculars, this is something that you're going to be able to pick out pretty easily in the nighttime sky. Oh, and maybe before we move around, Dan and Katherine, were there any questions that maybe want to come up? We're all good? You guys, perfect. I keep seeing questions coming up, so keep them coming, guys. That's awesome. All right, so taking the belt, we're going to go off to the right, and we're going to run into this orangey color star right here. And this star is called Aldebaran, and it's one of the eyes of Taurus the bull. So here's an eye, here's another eye, here's his little snout, and here's a horn up here, here's a horn over here, and his hooves are down here. And on the back of Taurus, where we had baby stars living in Orion, we have some toddler stars living on Taurus's back. And this little cluster of stars right here, called the Pleiades, and let's zoom in on those. And while the stars that were in the Orion Nebula were about 300,000 years old, these stars here in the Pleiades are about 100 million years old. So again, in people timelines, those seem like super old stars, but in star time, there may be like 3-year-old stars. So they're toddler stars that are going to preschool and starting to live their grown-up star lives. And if you've ever seen the logo for a Subaru car, like the car company Subaru, this is where their logo comes from, because Subaru is what the Pleiades are called in Japanese. So let's zoom back out. So let's see. So we have baby stars, toddler stars, regular age stars, kind of grandpa age stars. So where do we find a star that has gone past that into the next part of its life? Well, going up by Taurus's horn and just a little bit off to the left, or excuse me,
Hey,
to
Rachel,
the right. Yeah.
could you put up the actual like mythology, like illustration of Taurus? Some
Oh,
people are having a hard
absolutely.
time seeing the constellation.
Let's do, so there's Taurus the bull. So there's each of his eyes and his nose, and then each of the stars at the top is his horn. And then, as I said, I was joking about Betelgeuse being Orion's armpit star, but if you look at the picture, it's right in the armpit. So now that we kind of found those horns again, just off to the right of the horn, there's an object called M1, and let's zoom in on that. And this is also called a nebula. This is the Crab Nebula, but it's not a nebula where brand new stars are being formed. It's the nebula of a star that exploded, and this is the material that's coming off of the explosion. And so we actually know when this star exploded because Chinese astronomers had a record of a guest star showing up in 1054. And this guest star was so bright that for about 3 weeks after it appeared, it was visible during the daytime as well as the nighttime. And then after about 3 weeks, you couldn't see it in the daytime anymore. But then for several weeks after that, you could still see it in the nighttime sky. And what this guest star was actually the explosion of a really big star ending its main sequence or its regular life to move on to being a stellar remnant. And with telescopes, we know that the stellar remnant that's living here is a neutron star that is rotating 30 times in 1 second. So what does that look like in real life? Let's zoom, go forward a little bit here. All right, and I'm going to play this back and forth a couple of times, but this is the Crab Nebula, and this is over a few years. So there are 2 things that I want you guys to look for here. The first is notice the outer edge of the cloud is still expanding. So even though for us, this star exploded 1,000 years ago, we're still seeing the explosion spread out through space. The second thing is if you look right in the middle, you're going to see ripples. And that's from that neutron star that is spinning 30 times in 1 second. So again, something the size of Atlanta, that's 1.5 times as heavy as the sun, doing complete circles 30 times in 1 second is living here. So let's see what that looks like. And this is taken, I think, over 8 years. These are 8 years of pictures showing the expansion and showing those ripples moving through the clouds. Let me back up again so we can watch it. So again, seeing the expansion and then seeing those ripples of that star in the middle, I think is a pretty cool thing to be able to find. And so using this time of the year in this part of the sky, there are tons of stellar evolution things that you can find and see with a small telescope, and even some of them with just your eyes. All right, so let's put Taurus away. We're going to come back to Orion again. And instead of going right this time, we're going to go left. And we're going to use this to find some really bright stars that we can see in the nighttime sky. And we're going to come over and then do a half circle to find these stars. So again, back to Orion, taking that to the left, we run into this very bright star right here. And this is called Sirius. And Sirius is actually the brightest star we can see in our nighttime sky. And because it's so bright, it twinkles like crazy when the light hits the atmosphere. And so it looks like it's changing colors. So if in the wintertime you've ever seen something in the southern, like southeast, south, or southwest, and it's twinkling like crazy and changing colors, it's probably not a spaceship. It's probably just Sirius. And again, where the Andromeda Galaxy, just to kind of give you an idea about some distances, with the Andromeda Galaxy, where we're seeing that light from 2 million years ago, Sirius is much closer. It's only about 9 light years away. So it takes 9 years for that light to get here. So if anybody in the audience is 9 years old this year, Sirius is your birthday star. And the light that left Sirius when you were born is finally getting to Earth today, which I think is a pretty cool thing to think about. All right, so Sirius is actually the nose star of Canis Major, the big dog. So let's actually put up the pictures again so we can see that. So here are his little ears and then his little snout. And we're going to go up to Procyon, who is in Canis Minor, the little dog. And then we have Pollux and Castor in Gemini, the twins. And then we have Capella, who is in Auriga, the charioteer. So let's put the pictures down, find Orion again, and we go off to the left. There's Sirius. Here's Procyon. Here is Pollux and Castor and Capella. So even with the light pollution that we have in Atlanta, with the street lights and the house lights and the car lights, all of these stars in the southern sky, you're going to be able to go outside tonight, look up in the sky and find them. Now, there's one other thing I feel like we should talk about. So let me put the pictures back up. Some of these may seem a little familiar to you, where you have Cancer the crab, and Gemini the twins, and Taurus the bull, and Aries the ram. So for us as astronomers, we don't tell horoscopes, and we can't tell you how the stars are going to affect your life. But the zodiac constellations are important because they lie along something called the ecliptic. And this is the path that the sun and the moon and all of the planets take through the nighttime sky. So if we were to bring the sun back up and watch it move through the sky, it would move through these constellations. And so while we can't use them to tell horoscopes, the zodiac constellations are important because they mark out the path that the sun and the planets take through the nighttime sky. All right, so because we have other cool things to do, there's one last thing that I want to show you guys today. And this is going to be our last poll. So let me scoot ourselves back up. And we're going to take Orion, oops, and go back to the right to Taurus. So there's Aldebaran, and there are the Pleiades. And for our next poll, there's one planet that if you go outside tonight, you can find in the nighttime sky. It's this orangey red person hanging out there. So voting, who do you think that might be? Oh, it looks like we have a pretty strong consensus, and you guys are absolutely right. That is Mars. So let's go ahead and fly to Mars. And actually, if you are an early morning person, you can go outside in the morning before the sun comes up, right before sunrise, and Saturn and Jupiter and Mercury are all hanging out in the pre-dawn sky in the east. I'm more of a nighttime person, so I'll wait until they're ready to be up at night again before I go look at them. But if you're a morning person, you definitely should do that. And now we've made it to Mars. If we were going to Mars in real life, it would take us about 7 months to do that. And somebody just did make that trip, and that was the rover Perseverance and its little helicopter on Ingenuity. And I actually want to look at the other side of Mars, so let me, I should try, this is why I don't plan trips to Mars, because my landings are never right. So let me fast forward time and rotate a little bit so we can spin ourselves around to what I think are the cool parts of Mars. Oops. We're almost there. There we go. All right, so the first thing you may notice are these 4 giant craters over here, and these are actually volcanoes. Mars is geologically inactive now. The volcanoes are no longer active, but this volcano right here, Olympus Mons, is actually the largest volcano in the solar system that we know of. And to get an idea of how big that is, I found this picture that shows on the bottom, here's sea level, and here's Mauna Kea, which is a big mountain on Hawaii. It's one of the Hawaiian islands. And then you have Mount Everest, which is the biggest mountain on Earth. And then you have Olympus Mons, which is about almost 3 times bigger than Mount Everest. And it's a shield volcano, which means it's not tall and pointy, it's very broad. And so on the top part of the picture, this is France. And this is how big Olympus Mons would be if you picked it up from Mars and brought it back to Earth. It would fit over a really good part of France. The other cool feature, I think, that's on Mars is the Mariner Valley, which is this giant canyon system here. And if we did the same thing with Mariner Valley and we picked that up and brought that back to Earth, it would fit across the entire United States. So even though Mars has a diameter that's about half of the size of Earth, It has geological features that would be really big if they existed on this planet. And I think that's super cool. And so since we talked a little bit about Perseverance, I think it's a good idea to find out where it landed. So let's go ahead and zoom forward to a map. So here's a map that shows where some other landers, so Opportunity, Curiosity, here is Olympus Mons, here is Mariner Valley, and over here in Jezero Crater, that is where Perseverance landed. And let's zoom in on that. And in the chat, I want you guys to look at this picture. You may notice this winding bit of geography here into this big thing. If you were to think about something on Earth that might look like that, what does that look like to you guys? So go ahead and answer in the chat. And what are we hearing in the chat from our audience?
We've got a couple people saying river, a circle draining into a lake,
And that is exactly right. This looks like a dried up riverbed that went into a lake. So Perseverance is going to rove around and do investigations. We have two videos that we're going to post to the chat. One is the actual landing of Perseverance with its parachute and its rocket crane to help get it on the Earth. And also it's been doing recordings of audio stuff that's happening on Mars. I think the most recent one is it was lasering its first rock. And so you can hear the little clicking sounds of the laser shooting the rock, which I think is pretty cool. And so with that, I think that's going to wrap up the Star Talk, but I want to show you guys the handout that goes along with this. So we put some night sky tools. So the program that I'm using is Starry Night, and this is something you have to purchase, but there's a website called Stellarium that can do basically the same kind of stuff that I did with Starry Night if you want to plan your own planetarium type shows. And then also some other sites that have fun activities and ways to plan your night sky tour. We also gave you guys a couple of options for phone apps that we really like to help find things in the nighttime sky. And we also put information because under normal circumstances between March and October, we have monthly open houses at Hard Labor Creek Observatory where you can come and we'll show you our telescopes. We'll do in-person night sky talks. And this is really fun. And we really hope that once we can get back in person, we'll be able to see some of you here. And so the fun part for you is that we have a What's Up checklist. So if you want to see if you can go and find some of the things that we talked about tonight, you have this page here that helps remind you what we've talked about. And if you get a chance to go do that, there is the testimonial page on the Science Festival's website that we would love to see and hear about what you found in the nighttime sky. And if you found anything that we didn't talk about today, I would love to hear about that. So now that we know what's up in the nighttime sky, I think it's a really good chance for us to go ahead and switch over to talking about what might we find out there and talk a little bit about life in the universe and aliens. So I'm going to stop sharing my screen and Fallon is going to take over and start sharing hers.
Hello, thank you, Rachel. So if you guys can bear with me for a second, I'm going to share my blank screen and then get my presentation running. My computer's being slow. There we go. Do we see just the presentation? All right. So like Rachel said, we talked about what's up in the night sky. So we want to look at what can we find in the night sky? What's out there? It's a really big question for not just astronomers, but everybody. So I'm going to be using the chat function a lot. So asking some questions to get a discussion going, and Katherine and Dan will share out what some of you guys think. So starting off, what do we think life is? What does life entail? What is life? Just a big general question. Answer in the chat what you guys think. So Katherine, Dan, do we have any fun answers?
I like the first answer we got. It says anything alive. Life is when
That's a
things
fair
are
point,
living,
yeah.
Living organisms, things that grow. Yeah, keep the ideas coming, guys. Earth.
Yeah,
Life
this is more fun, guys,
doing
if you interact.
Yeah, anything made of cells,
Oh, that's a good one.
living and dying.
So we have a lot of really general answers. If there's any other ones that come up, please interrupt me and let me know. But some people were saying made of cells or need energy. So life on Earth, at least, is made up of something called organic molecules. And organic molecules are made of carbon atoms. So atoms you can think of as little Legos. They're the building blocks of everything in the whole universe, both life and inanimate things like my computer, your computer. And molecules are when you put those atoms, put those Legos together, you can make a bigger structure. So you put all these different types of things together and you can create things like life, like you and me. And life on Earth uses something called DNA, which is what we see a little cartoon of over here. And DNA is carbon based, so like one of those little Legos we were talking about, and it stores something called genetic code. And genetic code tells you everything about everything on Earth, all the life. So it tells me that I have brown hair and brown eyes and how tall I am. And it also is in other things like animals and plants that tells them this dog is this tall or this tree has this types of leaves. So life on Earth is made up of things like cells, but those cells are made up of smaller things that are atoms and molecules. So we really build up all these things together to create bigger life forms. So now that we know that life is made up of really small things like carbon, what does life need to keep living? Some of the other answers were life is what happens before you die, when you're alive. So what do we need to be alive? Let's answer in the chat again. What do you guys think?
Yep, we've had some water, food, energy, nutrients, the sun.
All really
Oxygen.
good answers. You guys kind of took my punchline of the next slide away, because we do need energy. And does our energy come from the sun? I think some energy does, like plants, they photosynthesize to make energy from the sun. We, as life on Earth, need water, and we need liquid water, right? Because if we can't drink water, we would die. And we need other types of raw materials. So just like we need food, that food is made up of things, made up of smaller Legos, smaller atoms like hydrogen and carbon. That's where we get all of our energy from. So our typical life on Earth needs these types of things to survive. But we're talking about what other types of life are there besides just humans? And even on Earth, there are almost alien-like beings called extremophiles. And these are a lot of really fun, crazy words that even I can't quite pronounce, like osmophile, Palyextremophile, zerophile. So all of these words are different types of extreme life forms that can live in different scenarios. Like a zerophile can live with almost no water. And a thermophile can live in really, really cold or really, really hot temperatures. And from these crazy words, you might think these must be really weird alien beings. But I can bet that many of you have seen extremophiles. How many of you have ever seen a cactus? A cactus is an extremophile, and it's what's known as a zerophile. So it can live in an environment that has very, very little water. And some species can actually live for a decade without water. And I don't know about you, but I can last maybe a whole day without water, and that's about it. So this is pretty crazy that cacti don't even need water for 10 years. And there are some more exotic extremophiles that live on Earth. This is another example, and this is called a tardigrade, or a water bear. This is one of my favorite extremophiles. I just think they're kind of fun looking. And it's what's known as a polyextremophile. So it can actually withstand many different crazy environments. So it can live in really hot or really cold temperatures. It can also live in really, really pressurized areas. So the bottom of oceans is really high pressure, or even out in the vacuum of space. And they're so crazy that they can live for hundreds of years, and they can live for 100 years without getting any energy. And I should mention that this picture is really zoomed in. They're not this big. They're only a couple micrometers across. So if you look on your ruler, the tiniest little marks you see, those are millimeters. And a micrometer is even smaller than that. So these guys you wouldn't even be able to see with your eye, but they're still really cool. So we've been talking about different life on Earth, but we want to know, what about life beyond, right? That's what you came to this talk about, to hear about. Life beyond our solar system, life beyond Earth. So where else might we find life? What do you guys think in the chat? Where can we find life in the universe? We see other planets, other moons, other stars. What do you guys think?
We've got exoplanets, other planets, exoplanets, asteroids,
All
Earth,
right.
Mars, everywhere except in black holes.
Okay, so you guys have some really big ideas. I like them. I also was thinking that exoplanets and other planets are a really good place to potentially find life. And so if we're looking to other planets to find life, we want to talk about something called the Goldilocks Zone. So the Goldilocks Zone probably makes you think of Goldilocks and the Three Bears. And you might be thinking, there's no way that's what this references. But in fact, it is. So for anyone that's not familiar with the story of Goldilocks and the Three Bears, Goldilocks goes into the bear's house while they're out on a walk, and she tries Papa Bear's porridge, and Papa Bear's porridge is too hot. She tries Mama Bear's porridge, and Mama Bear's porridge is too cold. But she tries Baby Bear's porridge, and Baby Bear's porridge is just right. So just like porridge and Goldilocks had the just right zone, the same thing can happen with planets. When you're too close to a star, like our sun, you're going to be way too hot on those planets. And when you're too far from a star, you're going to be too cold. And Earth just happens to be in the Goldilocks zone of our sun, which lets it be just right. So like I was saying, the Goldilocks zone is the technical term for saying it's not too hot and it's not too cold. And this is referring specifically to liquid water. Because like we are saying, you need water to live. You and I both do. All of these planets, all these plants, all these animals on Earth need water. So we want to find planets that are in the Goldilocks zone to try to find life that kind of looks like us or the animals or plants that we see on Earth. And the Goldilocks zone can be in different distances depending on your star. Rachael was telling us about the different temperatures of stars that exist and their different colors. And in this diagram, the green we see is the Goldilocks zone, the red is the too hot zone, and the blue is the too cold. So we see that for really hot stars, the Goldilocks zone is much further out. And for really cold stars, the Goldilocks zone is closer in. But each star still has a Goldilocks zone. So we can still have the potential to find planets that fall within this Goldilocks zone and maybe find life that uses liquid water. Now, do we think that the Goldilocks zone is the only place to find life? Do you guys think, are there any exceptions to the Goldilocks zone? Answer in the chat, and also if you think yes or no, what could these exceptions be?
Okay, so we've got majority yeses. Mars has some bacteria on it. Extremophiles are exceptions.
All right, so some good examples. There is another, you guys are right that it's yes, there are exceptions to the Goldilocks zone. And these exceptions exist if there are sources of energy other than the sun that can keep that planet or moon possibly, or maybe even asteroid, like some people were saying, warm. So where this water can exist. And you guys had some great examples, but I'm gonna show another one, which is Europa. Europa is a moon of Jupiter, and it's one of the largest moons of Jupiter, and it's actually one of the largest moons in the solar system. And Europa is another example of a place that liquid water could possibly exist. So Jupiter is our biggest planet in our solar system, and it really has a really strong gravitational pull. So when Europa is going around Jupiter, it's actually being expanded and contracted because its pull is so strong. So looking at this picture, it looks like Europa is pretty strongly made of ice, but because it's being expanded and contracted, there could be water underneath that ice. Like if any of you ever seen a pond that's frozen over and underneath there's still liquid water. I don't know how common that is to see down here in Atlanta, but you can take my word for it. It does happen. In the winter, there are big lakes that only the top will freeze and all the fish still live underneath in the liquid water. So Europa could possibly be an example in our solar system that life can exist other than just the Goldilocks zone. So we've been talking mainly about examples within our solar system, within Earth, where weird new extremophile life or regular carbon-based liquid water life can exist. But what about outside of our solar system, at different stars in the universe? What are the odds that life exists somewhere else in the universe? Do you guys think that life exists in other stars and other parts of the universe? So is there a consensus?
So far, we've got all yeses.
All right.
Oh,
I
some
also,
no's.
ooh, some no's. I also think that life could exist other places in the universe, for those of you that said yes. But for those of you that said no, we don't have proof of this yet, so you might also be the ones that are right. This is a picture of our Milky Way, and this is the galaxy that our sun lives in. And each of these little dots, and in the center where we see a very bright bar, that's where each one of these is stars. And we are talking about how each star has a Goldilocks zone. And in the Goldilocks zone, there can be a planet that is kind of like Earth and can have liquid water and life. So if each of these stars can have a Goldilocks zone, that's another chance for a planet like us. And there are hundreds of billions of stars in the Milky Way galaxy. So there's about 300 billion chances for a Goldilocks zone planet with life in our galaxy. But our universe is not made of just our galaxy. Our universe is also made of other galaxies. So to just give you a perspective of how big the universe is, if this is Earth, Earth is what's known as our solar system, so our sun and all the planets. And our solar system is in a group of other stars that have their own planets, and we find that group in the Milky Way. So this is our galaxy, but our galaxy is also within a group of other galaxies. And each of these galaxies also has all of these hundreds of billions of stars that each have planets like our solar system. And in the entire observable universe, each one of these little specks is a galaxy, just like the Milky Way. And each one of the galaxies has hundreds of billions of stars, hundreds of billions of opportunities for a Goldilocks zone to have a planet just like Earth. But we also know from our extremophiles that we might not need exactly like Earth to have life. So all of these different planets, all these different star systems, perhaps asteroids, like some people were saying, is a new opportunity for life to exist. And I personally think that the odds of having life around one of these stars is pretty high, just because there's so many of them. But we also think, just knowing by the extremophiles, that life might not look like you and me. So that leads us to our next activity, which is designing what we think an alien life would look like. And we're going to be looking at life specifically for different types of exoplanets. And I'm going to hand this over to Alex, who's going to talk about the different options for our exoplanets and lead us through our activity.
Okay.
Let me stop sharing. I think you can take the share privileges, Alex.
Yeah, you can draw. Okay, so we're going to be, yes, paper's fine. We're going to be going through this activity right here. You can access it somewhere in the resources. Hopefully you've had a chance to find some of these sheets, but just in case, is there a way to send this link out? Does everybody have this link? Cool, I'm seeing some of my colleagues nodding. Anyway, so you're going to find this sheet somewhere in our resources. And in the meantime, I have some pictures for you. So we're going to look at each of the different planets that's on that little create your own alien sheet. Okay, so let's go on a quick little tour of some of the options. You're going to pick one during this Zoom meeting, and we're going to just try to draw an alien that lives on that exoplanet. So here are your choices. Choice number, oh wait, where did choice number 1 go? Oh, well, I labeled them wrong. That's okay. Choice number 1, which is erroneously labeled choice number 2, is a very massive planet, more massive than Earth, and it's rocky. All right. So because it's so massive, this rocky planet has higher gravity than Earth. So just imagine if you went to this planet, you'd feel like you weigh as much as a hippo. You'd have the same mass, but you'd feel much heavier. So yeah, it'd be, yeah, you'd have to be pretty strong to move around. Alternatively, maybe we can try actual exoplanet number 2. This is another rocky planet, so it's kind of like Earth, but it's much less massive. So it has lower gravity, all right? So if you went here, man, you'd feel so light. You'd be able to bounce around You wouldn't have to be too strong to be able to jump and get around. You might have a thinner atmosphere though, because you won't have much gravity holding things together. All right, on to exoplanet number 3. Exoplanet number 3 is covered in some sort of liquid over its entire surface. Maybe it's water, maybe it's something else, you decide, but it's liquid. So if you want to get around, you probably got to swim or maybe fly, depending on what you want to do. But you're going to have some place to make your home each night. And just keep in mind, everything's covered in water on this planet. All right, exoplanet number 4. You thought the rocks were cool. You thought the water or other liquid was cool. Well, here you don't even have a surface. You're just on some sort of gas planet where everything is just cloud, like all the way down as far as you know. It might get pretty thick somewhere down there, but it's all just cloud and gas. And lightning, sometimes, because lightning's kind of cool. All right, how about exoplanet number 5? This one is covered in ice. And it has some great big fissures in the ice, great big gaps like this. Maybe there's water down there somewhere, maybe there isn't. Who knows? You'd have to crawl down one of those fissures to find out. It's also very cold over there. Exoplanet number 6 it has an atmosphere, but it's made of carbon dioxide. And it has ice at the polar caps and some dust storms and dormant volcanoes. That sounds familiar. I wonder where this is. Anyway, we're calling it exoplanet number 6. Exoplanet number 7 has 2 stars. Look at those two. We have them kind of up in the middle. They're both a little bit cooler than the sun. One of them's fairly dim, but it's still there. So that's cool. Maybe you get 2 eclipses every year. Who knows? Maybe you get lucky, or maybe you don't. Depends how things line up. But it's a nice enough place. It's a little bit chilly, so stars aren't quite as bright as the sun. Depends how close you are to it, though. If you're close enough, maybe you're within the Goldilocks zone and you're going to be all right. All right. On to exoplanet number 8. This one is what's called tidally locked. What that means is, whereas we rotate every day and we kind of see the sun go up and down and up and down, if you're on a tidally locked planet, like exoplanet number 8 here, then if you're on the sun-facing side, you're always facing the sun. You always kind of just orbit at the same rate that you spin. You're always facing the sun if you're on the sun side. Alternatively, you could go to the dark side of the planet, hang out on the dark side, never see the sun at all. Or you could travel. You could say, I miss the sun. I'm going to walk to the sun side. You walk to the sun side. There's the sun. I'm bored of sun. Okay, I'm going to walk to the dark side. Cross over the little place where it's kind of sunset all the time, hang out on the dark side. If you're really smart, you probably actually just hang right on the edge where the sun's like right barely visible and it's like either dawn or sunset all the time, which would just be kind of pretty. So yeah, that's exoplanet number 8. So I need a poll here. Could somebody get a poll up, please? We gotta pick one of these 8 lovely exoplanets. We're gonna try drawing an alien together. You guys can draw whichever one you want though, but I'm gonna be drawing one live with your feedback. All right, so pick a world. I'll draw for you.
I don't think we have a poll set up, so let's just spam the chat with whatever exoplanet number you would like.
Yep.
Majority of people are saying number 4.
Number 4. All right. There we go. Good choice. All right. Let's draw a gas planet alien. Okay. So this thing has to be able to move around in all the gas, right? So I'm open to feedback. I'm gonna start drawing something, but please bring in the suggestions, because so far I'm thinking something kind of wavy, right? Says it's got to get around somehow. Let me shrink that. All right, so it's some sort of wavy being, right? Maybe it needs a head, right? Give it some sort of little eye spots so it can see. Maybe it has big fins, right? So it can.
Somebody requests wings, Alex.
Wings. All right, we can put wings. All right, maybe instead of fins, we'll give it wings. What kind of wings do you want? You want membranes, or do you want to go really, really normal and just give it feathers? What do you want? What kind of wings? Or maybe something different. Maybe just like weird flaps.
We have elf wings, dragon wings.
Dragon wings it is. All right, we got you. We got our dragon wings on this strange little kind of flying creature. Well, dragon's making me think of like, I want to give it some horns and stuff now.
I'm sorry, I just love these answers. Someone said cow leather wings. I love it.
Cow leather wings. All
We've
right,
also
yeah,
got
I will
fairy
keep that in mind. It's
wings.
gonna have this like leathery texture to them, right?
All kinds of wings.
Yeah,
He has a different set for each environment.
that'd be pretty cool. So maybe it has like a little folded pair. Maybe it has like little display wings that it only brings out during breeding season or something. So it has like these little pretty, maybe it's like butterfly, folded up butterfly wings or something, right? Like, I don't know. But these
Well,
are like
and on the
special wings
butterfly
for
thing,
special occasions.
somebody suggested that it has camouflage.
Camouflage. Okay, it's going to be in a gassy cloud world, so it's probably going to be kind of colored, kind of a pale color, right? Maybe beige or maybe bluish. Either of those. It depends what kind of atmosphere you want, but I'm thinking a pale color of some kind. All right, so let's get this thing a little bit of color, right? And it's existing in its pale environment, right? I'll make it look prettier eventually, but we're getting the gist of it, right?
Yeah, we've got lots of suggestions. So we've got antenna instead of eyes, so that it can
That's a cool idea.
feel movement in the gas.
I like that. That's really cool. Let's try that. All right. So
we've got a tail and a beak as requested.
all right. Yeah, we kind of have the beak there.
Mhm.
And then a tail. I kind of have a wavy tail. Let me give it like a paddle, right? Like then it can have more directional control maybe. I'm still going to give it like little frills to kind of give it more control. All right, now it has little stalk eyes. Let me kind of blend that in here. But yeah, see, you just kind of make it do whatever you want it to do, right? You're just imagining this thing. There we go. And then it has these little like special fancy wings. I'm going to put a little bit of pale color on them, right? Just like these probably light up during certain times of the long gas giant year, however it may be, right? Who knows how close it is to the star, but yeah. Then if it ever wants to find its friends, it can flash the pretty wings, and then maybe they can see each other, right? The underside's probably a lot brighter than the top because it still needs to be camouflaged most of the time. But we'll get a little hint of the color underneath.
We have a request to give it a pet.
Okay, what kind of pet would you like? It'll probably need some wings too, won't it?
Yeah, should this be a friend that tags along with it or a friend that it can eat?
These are very good questions. Maybe it has antennae here too. Let's give it some extra antennae. Let me make it let's make it a like different shape.
Yeah, a friendly pet. Yeah.
Yeah. All right. Friendly little pet with little antennae.
And somebody suggested ladybug wings for this one.
Oh, that's cute. Okay, so we got the little wing shields, and then like the little, very, very fast moving little ladybug wings. It won't really need legs, I guess, because it's never gonna land. So I guess
well, somebody suggested feet so it can grab food.
Oh, that's a good idea.
So thinking about food, what kind of things do you think that these creatures would use for energy?
That's a good question. What is this thing going to eat?
Yeah, someone
really
says the
air,
air, gas. Photosynthesis. It would be like a floating grocery store.
Oh, that's fun. That'd be cool.
Lightning. It could use lightning as energy. It could use lightning as energy.
Whoa, that's cool. Yeah, I want a lightning rod. Okay, it's getting a lightning rod. It's just gonna have it like on its back. It's just gonna have this like big lightning rod thing that it can like stick up and just as needed it can stick it up and just get struck by lightning and like absorb the lightning. Okay, cool. Yeah, it's a lightning powered being that just floats around in the air. That's way too cool. I like that.
Yeah, it's we've got a recommendation of cat ears. I'd just like to throw that out there for all the cat lovers out there.
We can throw some of those on.
We've got a really good point by someone who said that it can't sit, so it should be able to stay afloat without expending energy, like when it's sleeping Therefore, maybe it should be able to reduce and increase its air pressure to go up and down.
Like some sort of air sac to maybe. That's a good question. Where do I give it an air sac? Okay. It might just keep that as like its underbelly. Will it be a big air sac?
Like a floating submarine, like a jellyfish.
Yeah. And like maybe somehow it's able to tell what kind of gas is where, or maybe it just rarefies it or something. Maybe it's strong and can like just change the density of it. Who knows? It has some sort of air bladder. And then the little ladybug guy. It's going to be kind of a pale ladybug, so it's not too showy. Anybody ever seen a yellow ladybug? They're out there somewhere.
You are getting requests for a lightning bolt in the background.
Oh, that's pretty cool.
Well, we've got a lightning bolt on his back. Oh, no, sorry. We've got a lightning rod on his back.
Yeah, that's so he can catch the lightning.
And he should have a music player playing the Beatles.
Gotta be entertained somehow, right? So like he has lightning, right? So maybe he has like a little, he just like plugs in his little iPod system and like here's his little he has an MP3 player because I guess he doesn't have an iPad because you can't maintain those out here, so it's just a really simple MP3 player. And then he's got his little earbuds and it's making that sweet music.
Just great question, Andrew. I'm not going to answer.
And this guy really likes it, so that's why he's around. He loves that Beatles music.
That was another good question. Is what does it do with the excess processed food that it is, or stuff that it's eaten for energy? Does it have to go to the bathroom at all?
Ew, yeah, probably. Well, that would go out here, but I'm not drawing that. I've given him back-turned ears because it's pretty windy when he flies, so the cute little cat ears have to face back, otherwise he would get an earful of like wind, so that would be too loud. But they can be fuzzy. They can be fuzzy little back-facing cat ears. So
we've got a request for a unicorn horn.
Why not?
The unicorn horn would be the lightning rod.
I'm gonna give
I'm gonna give the unicorn horn's gonna go on the friend. Because that's its lightning rod, all right? That makes so much sense, right?
Yes.
Yes. There we go. Let's see. Let's make it pink unicorn horn, right? Like, why not? There we go. That's how this guy catches lightning, with his cute little pink unicorn horn. But it's like full of magic pizzazz or something. I don't know. It's very conductive, so it's kind of special. There we go. It attracts lightning.
All right,
Okay,
so
cool.
We've got a couple suggestions for the name of this alien.
Oh, good.
So we've got John Lennon as its name, Draco, Artemis Fowl.
These names all sound strangely familiar.
Artemis Draco Lennon. Beatrix.
We can work with something like that. Yeah, I can't decide, so sure, let's make it all of them. Artego Lennon. Close enough. I'm just gonna tattoo it on this guy. So let's see. Artego How do you spell Lennon? Help.
Lennon.
Help.
Oh, it's an O-N.
Oh, thank you. Okay. All right, there he is. What about the little friend who I didn't really finish coloring? Let's see. This guy a little bit.
We don't want to draw farts. Stop it.
No farts. I don't draw farts. The whole gas. It's a gas planet. The whole thing's a fart. Whatever, right? Here, I can draw the background. The background can be like pretty clouds. So like, yay! Because they have to fly over the pretty clouds. And then it goes off into space too, so it's got to get some vague blues out here.
And a very strong request for a lightning bolt in the background, Alex.
Yes, okay. I am totally gonna get there once I color in a little bit more sky so we can see the lightning bolt.
And so while Alex is finishing the background and the lightning bolt, this was really cool, and I think this is great. And so just like with the What's Up sky tour. In the handout, this has all of the questions that you'll need. So what exoplanet did you choose? What does your alien look like? What does your alien use for energy or food? How do they move? Do they have any other features or abilities? And then what is the alien's name? And if you guys make these, we would love to see the pictures that you come up with and the descriptions of your creatures, and you can put them in the testimonials on the Science Festival's website. And we would love to see what you guys come up with on your own.
There's the lightning in the background coming in.
All right, and for the friend's name, we've got a couple suggestions. We've got a very strong suggestion for beetles.
That's a great name because it's like a little lady beetle.
A very strong suggestion for Dreary Motter.
Dreary Motter.
Yes.
All right. We're going to call it Dreary Beetle. Help me spell that.
Drarry.
Drarry. Dreary Beetle. Which I should know how to spell, and I also don't know. I don't know how to spell anything. Help. Is that 2 T's?
It's one, I think.
Okay.
Just one.
Okay, I'll write it underneath. Well, I tattooed the other one, so like. You're right. Okay, I'll write it underneath. Dreary Beetle.
Yeah.
Gotcha. Okay, there we go. And then little light sensitive eye stalks. There we go. All right, and there are our alien friends. Here, you drew one too, didn't you?
And we'll also post our creatures here to the testimonials, so you can remember, and if you want to show other people what we all created together, and you'll be able to find it in the testimonials after.
Yep, I will upload it there.
Yeah, we can just do it there.
Yeah, there we go. All right, we did it, guys. We're gonna save it as let's see, Artego Lennon and Dreary Beetle. There you go. We got you covered.
All right, so next up, we're going to switch gears a little bit here. So we have been talking about astronomy things for a while now, and bear with me while I switch over and share screens for everyone here real quick. And it's going to be finicky with me. So we have been talking about astronomy for a little while because all of us are mostly astronomers and we do astronomy things. But now we are going to switch it up and talk a little bit more about physics properties. So I have the Q&A partly open here and I'll get the chat up. So I'll try to keep an eye on questions going in the meantime. But moderators, if you guys want to jump in as well, if we get any chat things popping up. So what are we talking about here? We are going to talk about sound. So the title of this is Hello, is anyone listening? And I should probably introduce myself. My name is Andrew Couperus, and we want to understand how we're going to go about this activity. So you're going to make a string telephone like we have in the background, and we'll get into that a little bit farther into the activity, which Rachael will go over with you. But first, I want to explain how sound works. So what is sound? Well, there's all kinds of waves in the world. I'm waving at you right now. Hello, maybe you can see me waving. Or you've got ocean waves, like waves in water. That's a very common one. But sound is also a wave. The sound that we hear are sound waves. And so sound is just a wave, just like a water wave. So we can have ripples in water, kind of like, you put a little drop in water or in a pond or something and you get ripples going outward. Sound behaves just like that. It's just ripples in the stuff around us. So mainly I'm thinking about air here. So we've got some wave in the air molecules around us, kind of like a water wave. It travels through and then our ears can pick up that sound wave. So what is this actually coming from though? Well, fundamentally, sound is just a pressure wave, or how I like to think about it is vibration. So right now I'm talking and my vocal cords in my throat are vibrating. And those vibrations vibrate the air next to it, which moves along a little bit and bumps into the air next to it, which moves along a little bit and bumps into the air next to it. And so it travels along, everything bumping into each other, and you get this traveling vibration, basically, this traveling vibration wave that goes through the air. So in the example here, like if you had a speaker, speakers work the same way. That's probably how you're hearing it right now. You're not hearing me speak in real life. You've got some speaker that's playing what I'm saying. That speaker moves back and forth, and you get these pileups of air molecules, and then that pressure wave travels through as things bump into the things next to them, which bump into the things next to them, and it travels along until you can hear it. So you make pressure waves when you speak in the air around you. And then the little tiny hairs on our inner ear is what picks up those pressure waves. Those pressure waves go in, and at some point, the air bumps into the air next to it, and then that air bumps into the hair in your ears. And that picks up those little wiggles, and your brain interprets that as sound. So that's how we hear people talking and how sound works. But for all of this, you need something for the sound to travel through. Sound waves need stuff, or a medium is the term we use for it, something that it's propagating through, like the air. So we talked about water before. Maybe if any of you have ever been underwater, like if you've been swimming or in a river or a lake or something, you can tell sound sounds different underwater. And that's because it travels differently through the water. Yes, exactly. So just like light is kind of traveling through space-time in some sense, we have sound waves traveling through whatever medium. So we can have water, kind of like ripples, but with sound waves, or air, like I was saying, everything vibrates, or even string. Anything really that is just going to be able to carry a vibrations. Like with a guitar, you pluck a guitar string, and that guitar string vibrates, and that vibrates the air next to it, which vibrates the air next to it, and you get that wave of sound traveling to your ears to hear the music. So that's it traveling through stuff. Now I've got a question for you to answer. Because it's just vibrations, we can be the things, our bodies can be the things that sound vibrates. So can you think of a time that you've actually felt sound vibrations with your body? Maybe this was something really loud if you've ever been to a concert, or you're in a car with really loud music or something like that. You can feel the vibrations shaking your body almost. So I'll give you guys a second here to get your answers in the chat. And while you do that, I'll just tell you about my favorite, which is cats, because I like cats, and cats purr. And if you've ever had a cat sit on your lap, when they're purring, they're vibrating. And that vibrating you can feel in your body. It kind of vibrates on your lap a little bit. That's my favorite. Yeah, and we've got some other ones here. Heartbeat. I like that one a lot. You can actually, if you sit really still and quietly, you can actually almost feel that vibration of your heartbeat in your body. Or a skate rink. Yeah, loud floor shaking at parties. All these vibrations from the sound. Rock concerts, exactly. Great answers. I really like the heartbeat one. That's a good one. So you're actually just feeling the sound. It's kind of cool. So next, we're going to give you some animations to help visualize this. Here, we just have a simple speaker. So like I was talking about before, speakers just kind of move in and out. They oscillate back and forth. They wiggle, basically. And you can see a bunch of air molecules around our speaker. And as our speaker moves in and out, it bumps into the air and kind of pushes it out in a uniform ring, which bumps into the air molecules next to it, which bumps into the air molecules next to it. And you get this wave traveling along in the medium. And so this is the sound wave traveling like a speaker would in air, the way you're listening to it right now. Then we have a couple more to show you. So on the left is a more simplified diagram of this, where we just have one dimension now, one direction. And you have a speaker moving in and out, and you can see the sound wave traveling along that direction. So the speaker bumps some air, which bumps it next to it, and you see this traveling wave pattern. And you'll note the things actually kind of stay in place. It's just the pattern that's traveling, that vibration, that pressure wave that travels through. On the right is another interesting example. So all these dots would be air molecules or particles in whatever the object is. And you can see we have a little ball moving back and forth, and it causes these vibrations, these ripples, and everything around it, just like sound waves would in air. So this is very similar to the analogy I like to think of is if you've ever had a stick that you kind of move back and forth through the air really quickly, you can actually hear it. It's kind of like you whip the stick around, you can hear it whipping through the air. It's kind of like this diagram where it's moving back and forth and making those sound waves. And what makes those sound waves? I see the question in the chat, what things make sound waves? All kinds of things. Anything that causes vibrations or bumps into things around it. You know, I hit my desk. Maybe you can hear that. That's a sound wave because I'm hitting my desk and it's vibrating everything. All right. So next, we have a couple demonstrations to help show some really cool aspects of this. First, we're going to show you some waves traveling through a slinky. Now, this isn't part of the main activity, but if you happen to have a slinky at home, you can do this. Feel free to try it out yourself. So what's going to happen in this video is the slinky's going to be held in place, and then someone's going to tap it, and you'll see that wave traveling along it. So I'll play it here for you. And there you go. I'll play it a few times so you can get the view of it, because it's a short one. And so the slinky stays in place, but that wave is traveling through it. This is just like sound waves, where say that each rung of the slinky is like an air molecule, and it bumps into the thing next to it, which bumps into the thing next to it, and you get this traveling wave down the slinky. So feel free to try that out at home. You can wiggle the slinkies around in all kinds of ways and makes all kind of cool wave patterns within them. All right, so that's slinkies. Now we're going to get to my favorite part of this. So everyone pay attention. This is really, really cool what you're about to see. This next demonstration is called the dancing flames. So what we have in this setup, let me get it started. I'll pause for a second, is we have a tube, a metal tube, and it's closed off. And then we're going to play sound through the tube. And those sound waves will get trapped within the tube. But inside of it, we don't just have air, we actually have a flammable gas, and they lit up flames poking out of the pipe. So if we play this here, you guys probably can't hear this, but it's going to play sound through the tube. That's what they're doing. And that wave gets trapped in the tube, and you see the patterns of the sound wave in the flames because it makes kind of a pressurized area, and you can see those flames getting bigger where all of the air is being pressurized. And they have the hertz popping up here. That's just the frequency. So if you think about high pitch or low pitch, maybe those are terms you've heard of. So right now it's low pitch, so it's talking really low like this. And so they have a very deep sound in the tube, and you get these big long waves. But if we skip forward a little bit, they start to turn up the pitch, and now it's going really high like this. And you can see a lot more wave patterns in the flames of that sound trapped within the tube. And so all that's happening here is it's humming in the tube. It's just like, and it's a tune going through the tube. And you can get those wave patterns just seeing them in the flame strength. And they have to relight it here a few times. And then just getting higher and higher pitch. And then they lower the sound down or can turn it up louder. And you can see these flame patterns. It's a really cool demonstration. And I definitely recommend you check these out yourself. There's lots of videos you can find online of people playing songs through these setups. So you can see the flames dancing in tune to your favorite song, which is really cool. All right, that's the dancing flames. Now, one final thing, I saw some people mentioning this in chat, so I thought ahead and put it in my talk for you, is that you can't hear sound in space. Remember that sound needs something to travel through. It needs air to bump into, or it needs, wood if I hit the table or something. But in space, there's no particles really. There's not a lot of stuff. And so there's not really things for the vibrations to hit and bump into. So you actually don't hear any sound in space. So you have this nice diagram of an astronaut playing a guitar, but actually you wouldn't be able to hear it unless you were maybe on the space station and they had air in there, and they do have guitars on the space station. But if you're outside, there's no sound in space. So there's your fun fact. All right, so that's the basics of sound waves. Next, we're going to get into making the string telephone, and then I'll come back and talk a little bit about how the string telephone works with you and different ways of testing it out. So Rachael is going to hop in here and take over, and she's going to go over how to make the string telephone with you guys. So if you guys look at her video, she'll walk through making the string telephone.
Yeah, I think.
And I'll stop sharing I'll leave this up
no,
so you can see it.
I think that once I start talking, my video will come up. So what you're going to need is some paper or styrofoam cups, and then some string. I have yarn, and I also have butcher string for some reason. I'm not a cook, but this was in my home, so I was like, great.
Your video is also off, Rachael, if you want to turn it on.
I do. That would make this work a lot better. All right. Am I showing up now? All right. Cups, yarn, or like I said, I also for some reason had butcher string in my house. And then you have the choice for your attachments to either use paper clips. Oh, yep. I guess,
Yeah.
Andrew, can you please stop sharing so I actually show up? There we go. So I have toothpicks or paper clips. Either one is going to work. And then basically all you need to do is just attach your string. I would wrap it around the toothpick or the paper clip, whichever one you're using, and then tie a knot. And then with your cup, I found that my toothpicks were strong enough, but you may need to use a pair of scissors to do this. Just poke a little hole in the bottom of your cup and push your string through, and then grab it on the other end. So it comes through, and then what you're going to want to do is then pull it tight. You can kind of see that it pulls taut on the bottom of the cup. And then you do the same thing on the other side. So let me tie quickly. And in the handout, we have directions for doing this. And we also have listed a few experiments that you can try out at home with different prototypes. So since I have 2 different types of string, since I have paper clips as well, there are various ways that I could put this together. But then once your string is attached, you now have your paper phone and you are able to go on to the next part of the activity. So Andrew.
All right. Let me share screens again real quick here and we'll continue on. Okay. And I like seeing the chat, so I'm going to pop that out again. Yeah, wax the dental floss too. Like Alex said, that works really well too. If you don't have any string on hand, but you have a long string of floss, floss works great for this too. So like Rachel said, you can go through making your cups. And again, the instructions are in those handouts. If we could get the link in chat again too to the handout maybe as well, the moderators will put that in just for going through the steps of making this. Maybe you don't have the materials and you want to try this out later. That's totally fine. We've got some experiments to walk you through playing around with this. So what are you going to do with the string cup? Well, let's talk about string for a moment. How does this work? String carries sound, just like everything else. Like I said, air bumps into each other. I can hit my table and you hear the sound, and string can carry the sound. And string actually does a bit of a better job than air because string is much denser than air. It just has more stuff crammed into it because it's a solid, whereas air is kind of this free floating gas. So there's not as much stuff there to move around. So if we think about the air setup I had before with a speaker, maybe your speaker says, hello, and then someone's far away and it's just air and it's like, hello. And you can't quite hear it on the other end because it doesn't carry the sound very well. But string carries it better, but we have to be careful. If our string is kind of loopy like this, we'll run into problems. If I say hello on one end, my string carries that sound nicely, but I've got all these twists and turns in the string. And as the sound is trying to travel, it bumps into the thing next to it, it bumps into the thing next to it, it hits a turn. And it's like, oh, I've got to go over here now. And it kind of goes that way and it loses some energy in trying to do that to the air around it. So when your string is really floppy with your string telephone, it doesn't carry the sound very well because all the sound is trying to travel on the string, but it's kind of getting bumped around and lost with all these twists and turns to the air around it. And you don't really hear it on the other end as well. But we can fix this really easily. If you pull your string nice and tight with your telephone, so you keep it just a little bit taut as you pull on the string telephone, then you say hello on one end and all the sound shuffles along that same direction on the string. You don't have all these twists and turns and you lose less sound energy. And so you hear a nice hello on the other end. So you can test this out if you've got your paper cups. Would a metal wire carry the sound better or worse? It depends on the setup you're using. So this is actually kind of similar to how electricity works with metal wires. So it's very analogous to that. So it depends on the setup. So in your string telephone, you want to pull it a little tight, and then you can use your cup, speak into the cup and hear hello on the other end because that tight string carries the sound very nicely. So I'm going to walk through a little bit. Yes, plastic cups are totally fine. Paper cups, styrofoam cups, metal cups, any sort of cup is okay. Just anything, plastic ones, soup cans can work, yes. Styrofoam, paper ones, it's a bit easier to poke the hole in the bottom. If you've got a metal can, it can be hard to, maybe want a parent to help you out poking a hole in the metal can. But yeah, you can try different ones. You can test it and see what works. So the basic idea of how this works is you've got your setup with your string telephone, and on one end, you say hello. And then in the cup, that vibrates the air, which vibrates the cup. So the cup captures that sound. And then that cup vibrates the string that's attached to it. And so the sound travels down our string that's nice and tight now, remember, and you get it carrying it nicely to the other end. And then that string vibrates the cup on the other end. That cup on the other end vibrates the air again, and then that air goes and those vibrations carry into the ear of the person on the other end, kind of holding the cup up to their ear. So you get the sound traveling that full chain nicely, and you can hear the sound with the string telephone better than if someone was just trying to talk to you. And why do we use cups? We were just talking about the cups. The cups capture the sound nicely and they amplify it. So like we said, you can use metal cans or a paper cup or styrofoam cups here. Just the way this works really nicely is if I put the cup over my mouth and I talk into it like this, that captures all of that energy that I'm putting out with my mouth, all of that sound. And so it makes it really loud. It carries it well. And then on the other end, it amplifies it. It's kind of like a speaker. If you've seen speakers before, the cups are kind of shaped like speakers, and you hear all of that sound nicely with it propagating around to the other end. So that's sound, the basics of sound, and the string telephone. That's our last main activity that we have for you today. We do have a little bit of time left, so we're happy to answer questions, keep going through these activities, talking about life on planets and all these things. And I recommend following the handout for the string telephone activity too. There's lots of fun experiments in there. You can try it taut, try it slack, try different combinations of things to see how the sound behaves.
Yeah,
and with that, I'll stop sharing, and Rachel, you can take over.
Yeah, and so for the last part of the activity, we just wanted to have kind of an open Q&A. So if there's anything we talked about that you guys wanted to discuss further, and I also wanted to share with you a survey for the Science Festival organizers to give them feedback, since this is a new format for the Science Festival. And if you do the survey, you get entered in for a chance to win a DoorDash gift card. And since I haven't been to a restaurant for over a year now, I'm a big fan of DoorDash. So it's a nice thing to do and it's helpful to everybody. So yeah, if you have questions that you would like to ask us about any of the activities that we've done or other physics and astronomy things, we will be happy to answer them. And we also just want to thank you all for joining us today. This has been really fun. And I'm really looking forward to, again, in the testimonials, please share, if you've participated in any of the activities, please share what you've done there, because we would really like to be able to see and hear about your guys' experiences. So DoorDash survey, testimonials, and does anybody have any questions for us?
Anything about space, astronomy? We're all astronomers here, so we can answer all your fun alien questions. And physics things too.
And thank you all for being such good participants in the chat. That has been so fun. Yep. So if you don't want to stay and chat with us, you're free to go. How are stars named? This is a really good question. So there are actually two ways that stars are named. The first one is that there is a naming system where they basically get the genitive form of the constellation, and then they get a Greek letter based on how bright they are. So the brightest star gets to be Alpha, the second brightest star gets to be Beta, and then so on and so forth. For the really bright stars, while most of the constellations end up having Greek and Roman names, the stars end up having Arabic names. And I think this had a lot to do with differences in what was happening scientifically during times where in Europe, people were afraid to take baths, but in other places, they were still participating in science. And so a lot of the stars that have proper names have Arabic names, while constellations have Greek and Roman names. But scientifically, they have designations by a Greek letter and then the constellation that they're in. So let me see. Somebody asked about besides the Orion Nebula and the Crab Nebula. So in the summertime, there are two really good nebulae called the Lagoon and Trifid nebulas that are hanging out. So Sagittarius, well, actually, since I can do time and space, would anybody like me to show you how to find a summertime nebula, since we aren't seeing each other then? I'll be happy to do that if that's something people are interested in. Okay, so let me go to the summer. And let me share my screen again. make it dark. All right, so this is, I've set this for July, which is kind of the middle of the summer. And let's see, share. There we go. And the two big constellations that are up in the summer sky are Scorpius and Orion. So you can see Scorpius, here are his little pinchers. Here's his back and his long tail, and his stinger star, Shaula, is there. And then he has this orangey red star on his back called Antares, which is named this because if Mars is up at the same time, they both look like this, where they have this nice orangey red color. And so Antares means against Aries, or basically it means not Mars. So scientists are like, yeah, that one's not Mars. But right over here is Sagittarius, who's shaped like a teapot. So you can see the little body of the teapot. Here's the handle, the lid, the spout, and when it gets all steamed up, the Milky Way comes out. But right above, now let me see if I can, let me search here. Is the Lagoon Nebula. So let's zoom in, we'll magnify in place. And the Lagoon Nebula and the Trifid Nebula are right next to each other. So the Lagoon Nebula is an emission nebula, which means that it's red because there's a lot of hydrogen in there. And when electrons get excited, they don't care for that, and they're lazy and they want to come back down to rest as soon as possible. And so they get rid of that extra energy. And one of the emission lines in hydrogen is at a red wavelength. So basically, if you see red in space, that is hydrogen screaming at you saying, hello, it is I, hydrogen. And then right above the Lagoon Nebula is the Trifid Nebula. Let's zoom in on that one a little bit more. And it's called that because it has three parts. When this was discovered, I think it was in the 1700s, they saw this bluer portion, which is a reflection part of the nebula, the emission part in the red, and then there's really thick gas and dust clouds that block out the light from the baby stars living here. So they actually thought it was three different parts and three different things instead of one object together. But so in the summertime, these are two that are really nice to find with a telescope. Unfortunately, there are no nebulae that you're able to see with just your unaided eye. But in the summer, so Orion, the Orion Nebula, and actually, let's go back to today. I had to pick and choose what I showed you because we only had a certain amount of time. But back in Orion, if you zoom in right off of Alnitak, which is one of the belt stars, there are a few more nebula hanging out here. And one of them is a pretty famous one. Oh, come on, where are you guys? Is the Horsehead Nebula. So let's go ahead and we will zoom in on that. There we go. And you can see that it looks like a little horse head, and that's why it got its name. But right above the Horsehead Nebula is the Flame Nebula, which is another really nice nebula. So the Lagoon and Trifid nebulas are really nice to look at in the summer. If you do have a telescope, Orion is really good for finding these nebulae, though, because they're right next to bright stars. Because right there is Alnitak, and so just right off of there, up here is the Flame Nebula, and then right below is the Horsehead Nebula. And they're really cute, really fun things to look at.